All right, so we're going to go over this page 53. The most common things that people struggle with on these are the conditions or the assumptions, which, that's your get real. Okay. I can't help you with this, people. This is just kind of something you got to memorize how to do. Okay. I mean, there's a song for that and such, and I've been singing it to you as we've been doing it, but you got to figure that out. Okay. And then the other thing that people struggle with, typically the most, and I think I'm going to go over a problem today that will kind of clarify this, is which standard deviation to use, because it depends if you're talking population or sampling distribution. All right, so these are the most two common things confused, and so I hope I get to hit those two today. All right, so let's go over this. Page 53, our chapter 18 homework part 3. So first, we knew this was a sampling distribution because it talked about samples of 100 students. What do you think it would have said if it was talking about the population? It might have told us it's a normal model or something, and we would have had to have that. But it would have said, what's the probability that a student, not a certain proportion out of 100 students or that kind of thing. It would have been talking about a single student, a distribution of students. Okay. So let's do let's look at all the details you need for your conditions. So we know random, independent, and large enough. So we want to say use context. Do not just write RIL. That's wrong. Okay, I will just make a big old X if you just write RIL, because nobody knows what get real stands for. That's me thing. So randomly selected 100 students. Okay, so it randomly selected 100 students. And so see context, students. Okay, independent. So what's the idea? What is the goal of independence? To conclude that, like, independence tells us that what?
What we have will change.
Good. Your probability, what you have, your sample, taking that sample out isn't changing the probability. Okay, so keep that in mind. Your sample isn't changing the probability, because that means it is small enough. So see, independent, it's a small sample, so it's not changing the probability. This one's a less than. Independent is a less than. So it's reasonable that your 100 students is less than 10% of all university students. I'm kind of making that assumption. Okay, so I'm thinking there's at least 1,000 students or more at that university. Okay, but independent is the less than. And then, of course, large enough is the greater thans. So random and independent is the same if it's a mean or proportion problem, either way. It's large enough, it depends if it's a mean problem or a proportion problem. Okay? Then the rule effect is changed. It is large enough if it's a mean problem, if your sample size is greater than or equal to 30. It's large enough if it's a proportion problem if you have at least 10 successes and at least 10 failures. Okay, so that's what we got going on there. All right. And then here on the second one, it says what's the mean and standard deviation of the distribution. So there was your mean. And then, of course, for standard deviation of p-hats, you have the formula. All right. So at this point, I wanted to kind of mention to you a common question I've been seeing, and people don't really know like how to answer it. So I was going to tell you, and I've just figured this out. Somebody asked me a question fourth period today, and I was like, hey, I think that kind of makes sense. So what do we typically do if we are asked to describe the distribution? What things do we need to do when I say describe the distribution? Yep, your shape and outliers. Now on this, we may or may not have outliers to discuss. I mean, they would specifically probably mention something about that. And then what's C? Your center and spread. Okay, so let's talk about this. The way that we can kind of justify or discuss the shape, if it's a sampling distribution, that's your get real. Because how do we conclude our get real? What's our conclusion to get real? Yeah, approximately, because look at those pictures over there. Are those actual normal models? No, they're approximately normal models. So see, your get real is going to be for your shape. And then what would we indicate for a center? Of course, we would actually compute the mean. And then for our spread is typically what? That standard deviation. Okay, so if you are asked, and you will be asked on the reviews and some of those problems to describe the distribution, then you need to do shape, center, and spread. And so your shape is coming from this get real and saying that it's approximately normal model. Okay, because people were asking me, when do I need to get real? Anytime you use a z-score, you got to get real because you can't use z-scores unless you have your approximately normal model stuff. Okay, back to this. So there was that. Then you did some math and you came up with those numbers or something close to it, depending on how you rounded. So here, this was a sampling distribution of samples of 150 apples. So let's check our get real again. Random 150 apples says it was randomly selected. I think it's reasonable. Our 150 apples are less than 10% of all apples on the truck. At this point, I want to point this out and remind you. When you are saying this independent thing, this is kind of you saying, hey, person reading my problem, this is the population that I'm talking about. The population is all Americans, or the population is all university students, or the population is all these apples on the truck. Okay, because N is less than 10% of the population. Okay, so that's your way of kind of saying, hey, here's the population. All right, and then large enough, since this was a proportion problem, there was that, and approximately normal model applies. There's your mean and standard deviation. Okay, questions there? So top of the next page, we kind of already did this yesterday, talked about that, but let's discuss these problems here, number 28A and 28B. So here's a picture of both of those. All right, 28A is filled with all the workers. I guess this was American workers or something. So here's a worker and how long that person worked at that job. Here's a worker and how long that person worked at that job. So there's tons and tons and tons of data in here. Why is it skewed right? What? Okay, more people are leaving around, only staying about 6.2 years, but what's making it skewed? Yeah, you have a few of these upper outliers that people stayed at that job their whole career and worked there a whole lot of time. But it's just, that's less frequent than those people who stayed less time. So the way I wrote that was, some people could work at a particular job their whole lives, and hence you have some upper outliers. Okay, now let's look at what 28B is discussing. So what do you notice the difference between the 28A and the 28B pictures? Okay, one's approximately normal and the other one is skewed to the right. Okay. What made this 28B's shape different than the one up above? Good. These are X bars. This X bar came from randomly selecting 100 of these and dropping down an X bar. Randomly selecting another 100 and dropping down the X bar. And we know, is 100 quote unquote large enough to make it look normal? Okay, so therefore, the question is this: do I have the right to tell you the proportion of Americans in this yellow shaded area that worked 10 years or higher? Can I tell you the proportion of Americans that worked 10 years or longer? You can't. Why not? Because this is not normally shaped. Good. But look down here below. Can I compute the proportion of averages of 100 people who average more than 10 years? Yeah, see how that's stated a little differently. I can compute about the averages of 100 people, but I can't talk about individual workers. Okay, very good. So that's what was going on there. Then we skipped 29 and we come on over here to this one. Okay, so this problem, I hope that this problem is going to help you understand the other most commonly misunderstood idea, and that is, which standard deviation should I use and why? Okay, so let's take a look at this one. So, hey, do you wonder why you have air, like do you not think about your potato chips and think you're getting gypped off because it's like only partly full and that kind of, have you ever thought that? Okay, that air in there is on purpose. Why do you think it's in there on purpose? Yeah, as a protection so the chips don't get crushed. See, so you do actually get how much they say you're getting. They just have lots of air. They have the air in there and seal that in there to protect it. Okay. But according to this, you will get on average 10.2 ounces with a standard deviation of 0.12 when you pick a bag off the shelf. And they say it's normally distributed. So let's take a look at this picture right here. They say that these bags of chips are normally distributed. This is the population, a bag of chips, a bag of chips, a bag of chips, and they average 10.2. Look at this symbol, mu, that with no subscript. Why? Because this is the population. Okay, and they say that the sigma, that standard deviation is 0.12. So this is the population, mu, and the population. So that's where they're centered. Okay. And so they want us to find what's the probability, what proportion of chips are you getting shafted on and getting less than 10 ounces? And so then what standard deviation would I use to compute this z-score? My 0.12. Okay, very good. So see, that's what I have going on here. I've got my 10 minus the 10.2 over the 0.12. So that's about 4.78%. I wish I had rounded these so that it was like 5%. So it's pretty much about, if you think about it, about 5% of the bags you pick off the shelf, you're going to be getting the shaft. You're going to be getting not what you paid for, less than what you paid for. Okay. So this next question isn't really a sampling distribution question. It kind of brings back old info. What's the probability none of those three are underweight? So that means all three are good. So not underweight, and the second one's not underweight, and the third one's not underweight. If this had been 5%, it'd make a little bit be easier to understand. If 5% are underweight, what proportion are good to go? Yeah, so it'd be like saying 0.95 times 0.95 times 0.95. Okay, but it's a little bit trickier. So this is kind of a throwback to what we did for Christmas. Now, here comes the main idea for today of this kind of idea I want to help you understand. This says, hey, what is the probability that not just one bag, but the average of 3 bags is below the 10-ounce mark? Okay, so this is now not talking about a single bag. What is it talking about? This average, this average of 3 bags. Okay, so it's talking about an average of 3 bags. Okay, so where's the center of, so we have this sampling distribution, and you drop down 3 bags and you average them. You drop down 3 bags and you average them. You drop down 3 bags and you average them. And you do have some that are below 10 ounces. Okay, so my question is, here's my first question for you. What word in the question, or how do you know that question in part C is talking about this blue distribution, this one, as opposed to the population? This sampling distribution as opposed to the population, okay? So odds tell the evens. How do you know it's talking about that sampling distribution instead of the population. Go. So when you read a problem, how do you know you're then talking about the sampling distribution and not just the population? Okay. Matthew back there, who's even? Okay, Eva. Seems like every single time I go to you guys, it ends up being you. Okay, what you got?
So we know that it's sampling because it's talking about 3 bags versus talking about 1 bag.
Perfect. We know it's sampling distribution because it's talking about 3 bags. But furthermore, it says what's the average of those 3 bags. And so when it's talking about the average of those 3 bags, it's getting an X bar of 3 bags, a sample mean of 3 bags. Hence, this situation right here, your X bar of 3 of these. Okay, now taking a look at this, tell me about this standard deviation of this second one. What's the standard deviation of this right here, of these X bars? Is it 0.12? No, this is 0.12. This one is going to be smaller. How much smaller? It's going to be your 0.12 divided by the square root of 3. Okay, so that's how you know which standard deviation to use, because it's talking about those averages of 3. Hence, the standard deviation I use is that smaller one there. Okay, so then look at that probability. It's pretty small, 0.0019, about a fifth of 1%. And in fact, if I zoom this in, look here. So if this is about 5% here, then, if this is about 5%, look down here, to have 10, an average of 3, look at how little that is right there, see? Because the whole thing sucked in, there's less averaging below that 10-ounce mark. Look at this one. This one's the next question. It's going to be a whole entire case of 24 bags, and it's going to average 20. So how did we get the standard deviation for this sampling distribution with 24 bags? Yeah, we took 0.12 divided by the square root of 24. So that's really small. Hence, how many samples do you think are out here? What's that probability out there? Pretty much 0. So take a look at what we have. Here is there's our one for 3, and here's our one for 24. The z-score is negative 8.16. 8 standard deviations down there is 0% chance. So that's what happened. See from this picture? Look, right there. Does that look like doesn't this look like a ridiculous amount of standard deviations below the mean? Yes, 8 standard deviations below the mean. Okay, so in summary, what you have is the 3 different situations: the population and its standard deviation versus average of 3 with a smaller standard deviation, average of 24 and its standard deviation. Okay, so I hope that cleared that up for you. Now, let's take a look at this next one and have a little discussion about these shapes. So these are tips, and so we have tips that are skewed to the right. And so here we go. Here's this situation. Tips that are skewed to the right. Why do you think the tips, like for real, if you go work, why might the tips be skewed to the right? Yeah, a whole lot of people don't pay, but you know what? Your mom comes in and she gives you a good tip there. Okay, your grandmother comes in and she gives you a good tip. Okay, so every once in a while, you're going to get somebody who was just amazed at your perfect service and gave you a big old tip. Okay, so it will average. So the average it said is 9.6 with a standard deviation of $5.40. Okay, so the population of all your tips averages. Now, do you have the ability to compute this probability above $20? No, you cannot because it's not normally shaped. What happens if I have samples of size 4 or 10? Can I compute that probability right there? No. Why? Samples of 4 and 10, did they fix the problem and make it normal yet? No, they did not. Okay, so that's what we said on our answer, is that here, okay, A, we can't do it because it's not normal. B, N is 4, it's not normal yet. C, N is 10, not normal yet. Okay, but top of the next page, N is 40. Now what's happening? Now, when N is 40, okay, so let's say we got N is 40. Is it large enough now to where I can compute? Yes. Okay, the average of these X bars, because these are X bars in here, that's an average of 40 tips. Average of 40 tips. Average of 40 tips. So it centers at 960 still. But how about this standard deviation? It's that 5, it's small. 540 divided by the square root of 40. Because see, look, compare it to the top, see? Much smaller standard deviation. So you have to use that smaller standard deviation. I'm going to tell you the thing that caught me on this was here. That's what threw me. I have to say, oh, 960 is the average tip. Well, if I'm going to make $500 over the course of 40 tips, how much do I need to average to make $500 in 40 tips time? So right here. So in order to make 500 bucks, so if I'm going to budget for $500, I'm going to have to make $12.50 on average per tip. So that's what I did my Z-score. $12.50 minus the mean over the standard deviation. And look at that probability, 0.0003. What you think? Should you expect that much to come in? Yeah, no. Not going to happen. So do not be planning on 40 tips giving you $500. Okay, but the catch was your standard deviation is now 85 cents, not $5.40. Okay, because I'm not talking about the population up there. All right, part B is like stuff you've already done. Remember, the top 10% is the bottom 90%, so that's a Z-score of 1.28. And then you can solve for X. Okay, so even on the best 10% of weekends, you're only going to average about $10.70 a tip. So from there, you can figure out how much to budget. All right, there it goes. So does that help make any sense more on like when you use that population standard deviation versus when it changes? Okay. So see this picture down here, the standard deviation of that one was only 85 cents. So it wasn't very likely you'd be making more than $500. Okay. The last thing that I wanted to mention to you, because it was my bad, I should have told you yesterday, okay, is an issue with this down here. So will you turn to your warm-up? I think it's on page 57. And take a look at number 2. Did anybody check their conditions on this and be concerned? So random. Okay, random. So we are told, so this is ACT scores for Ohio students. So we are told that is a random sample. So randomly selected 25 students. Independent, what would I say? Independent, 25. is less than 10% of all Ohio students that take the test. Large enough. This is a mean problem, so what's large enough? 30. Wah, wah, wah. Therein lies the problem. 25 is not greater than or equal to 30. So what the heck? Okay. So what I wish I had done, and I've got to make myself a note, I need to put in there that, guess what? This is a fact, actually. Standardized tests such as ACT, SAT, AP scores, your EOCs, all of that kind of stuff, they are standardized, meaning the standardized normal curve. So all standardized tests have a population that is normally distributed. So that was a tidbit of information that you didn't know, that this problem made the assumption that you might know. On AP, they certainly wouldn't expect, I think they would make sure that that's not a, is that a cultural bias of some sort? I don't know. It's just a bias that you don't know that standardized tests are not normally distributed. So they probably would have told you that on an actual AP test. Okay? So the question is, how do we write that out? We say, okay, so on this number 2, you would do your little random, you would do your little independent, and here's how you would handle this issue. For large enough, you say, oh no, 25 is not greater than or equal to 30. But ACT tests, the population, ACT tests, because they're standardized or whatever, are normally distributed. So since the population is normally distributed, we know we're okay. All right, so go back to here. So the approximately normal model applies. Okay, so keep that in mind. Since the ACT tests are normally distributed, because it's a standardized test, then we're good to go, even though it's a small sample. All right, so that is the end of me going over stuff. I'm going to go around for the rest of class and answer any specific questions you have. But for now, you're going to work on those things there. Okay.